You are listening to The Vocal Technologist. Spoken tech for your ears.
What if the autonomous coding tools writing your company's software were also quietly leaking millions of your corporate secrets to the public, completely breaking your user experience, and forcing your senior engineers to clean up a sprawling mess?
It sounds exactly like the premise for a dystopian tech thriller, to be honest. But when you look at the raw data coming out of the engineering world, well, it is precisely what is unfolding right now.
Spot on. You are listening to Vocal Technologist, and I'm your host, pulling apart the immense tension happening in data engineering. We're building petabyte-scale infrastructure to feed these autonomous agents, essentially handing them the keys to the kingdom.
Yeah, and then watching in absolute horror as software quality plummets and security risks just explode.
Exactly. So we are going to explore how this infrastructure actually works and why giving it a mind of its own is creating pure chaos. Because as a tech-savvy mate, I have to tell you, it is straight up wild out there.
It is a critical tension to examine because to truly understand the failure of the agents, you first have to understand the sheer magnitude of the systems feeding them.
Right. The underlying plumbing.
Exactly. The underlying plumbing of the internet has fundamentally changed to support these massive artificial intelligence models.
Absolutely. Before we unpack the chaos caused by the agents themselves, we have to look at the staggering volume of data being moved just to make these systems possible. Take Reddit, for example.
Oh yeah, their massive migration.
Yeah, they pulled off a monumental migration of their Apache Kafka fleet.
Yeah.
For context for you listening, Kafka is basically the central nervous system for their real-time data. Every upvote, every comment, every single stream goes through it. But Reddit migrated over 500 brokers from Amazon EC2 to Kubernetes.
And doing that at petabyte scale is historically fraught with risk. I mean, a broker in Kafka is essentially a server that stores and serves that streaming data.
Right.
So when you have over 500 of them, moving the entire operation to a new orchestration system like Kubernetes, well, it usually guarantees some level of downtime. Or worse, corrupted data. It is a highly volatile operation.
I reckon sysadmins would be sweating bullets over a job like that. But they achieved zero downtime and zero data loss. They did it by introducing something called a DNS facade for connection abstraction.
Which is incredibly clever.
It is. I look at this and think it is like changing the engine of a commercial jet while it is flying at high altitude, but doing it by secretly building a second engine right next to the first one before turning the old one off.
That is actually a really accurate way to visualize it. The DNS facade acts like a fake address book. The client applications that are producing and consuming the Reddit data keep sending their requests to the exact same address they always have.
So they have no clue.
None at all. They have absolutely no idea underlying infrastructure is shifting. The facade simply routes the traffic to the new Kubernetes cluster behind the scenes.
Which is brilliant. And they also use a clever trick with the cluster size itself, right?
Yes, they double the cluster size using higher ID EC2 brokers. By moving the active data to these newly created higher-numbered brokers, they temporarily freed up the low-numbered slots. Yeah, that allowed them to seamlessly transition those specific original identifiers over to Kubernetes without breaking the sequence.
And to manage all of this, they forked the Strimzi operator. An operator is basically an automated traffic cop for Kubernetes, and they customized it to manage a mixed operation of EC2 and Kubernetes simultaneously. An absolute mammoth effort.
It really is. And it is not just Reddit. You also have Snap migrating their A/B testing data pipelines.
Oh, right. We're talking about processing over 10 petabytes of data per day. They moved from CPU-based Apache Spark to NVIDIA GPU accelerated Spark on Google Kubernetes Engine.
The shift from central processing units to graphics processing units for data pipelines is a profound mechanical change. Central processing units are like a single mathematical genius.
Okay.
They're great for complex sequential logic where step B rigidly depends on step A, but graphics processing units are entirely different.
They are more like 10,000 high schoolers doing basic addition at the exact same time, right?
Exactly. They excel at parallel processing, doing thousands of simple mathematical operations simultaneously.
Which you need at that scale.
Absolutely. When you are churning through 10 petabytes of daily A/B testing data, trying to figure out if a red button gets more clicks than a blue button across billions of user interactions, well, that parallel processing is absolutely essential.
And the results really speak for themselves. Snap got 4 times faster runtimes and a massive 76% daily cost savings. So we have these huge pipes pumping petabytes of data efficiently. But here is the rub.
Right.
You can move the data all you want, But how are we actually storing and processing it locally so autonomous agents can easily read it without instantly overwhelming the physical hardware?
That is the next logical hurdle. You can pipe the data to the machine, but running complex artificial intelligence models against it is incredibly resource intensive.
The machine just chokes.
Exactly. This is where we see clever software innovations stepping in, like GreenBoost. It is an open source Linux kernel module and what they call a CUDA shim.
Okay, a CUD shim. I reckon I know what this does, but walk us through how that actually interacts with the physical hardware. Is it basically a translator piece of software sitting between the code and the graphics card?
You are on the right track there. When you run large artificial intelligence models, your main bottleneck is usually the video random access memory.
The VRAM.
Yes, the VRAM on your graphics processing unit. It is incredibly fast but very expensive and limited in physical capacity. So GreenBoost acts as an interceptor.
Oh, wow.
It intercepts the memory allocation requests at the software level before they ever hit the hardware.
So it tricks the hardware into thinking it has way more memory than it actually does.
Precisely. It extends the available VRAM by transparently offloading the overflow data to slower memory tiers. It pushes the excess onto your standard system RAM or even your NVMe solid-state storage drives.
That is wild.
It is. It allows developers to run massive models on smaller, cheaper graphics processing units without requiring them to change a single line of their original inference code. You trade a slight bit of performance speed for a monumental increase in memory capacity.
That is a massive cost saver.
Yeah.
Now, moving from those sneaky hardware tricks to actual storage, I noticed this hilarious push to turn absolute everything into a PostgreSQL database.
Oh, yes. That trend is very real.
Right. There is an open source tool called pgit that turns your entire Git commit history into a PostgreSQL database with built-in delta compression. This lets developers, and more importantly, autonomous agents, instantly query the entire codebase history using standard SQL commands.
The underlying logic there is quite powerful, though. Git history is typically accessed through specialized command line tools.
Which can be clunky.
Very, and agents can struggle to navigate them smoothly. By structuring that history as a standard database, pgit applies delta compression, meaning it only stores the changes between files to save space.
Makes sense.
But more importantly, it makes complex codebase analysis instantly accessible to any tool that speaks standard database language.
And it does not stop there. A system called TigerFS actually mounts a PostgreSQL database as a computer file system. It replaces fragile file-based coordination with full ACID transactions and version history. Because apparently absolutely everything is just a PostgreSQL database now, which is exactly as terrifying as it sounds.
It is funny, but it speaks to a deep industry desire for structural reliability. A traditional file system lacks strict guarantees about concurrent access.
Right.
So if an agent and a human try to write to a file at the exact same time, or if the power fails, the file can corrupt easily.
Which is where those AC key properties come in. Atomicity, consistency, isolation, durability.
Exactly. It is a mathematical guarantee. By mapping a file system to a database, TigerFS ensures that when an autonomous agent reads or writes shared data, the transaction either completes entirely or fails entirely.
So no half-baked files.
Right. It does not accidentally leave half-written, corrupted data in the environment.
Which makes perfect sense when you consider platforms like Metabase. They provide an open-source business intelligence platform that connects to all these different databases for SQL and no-code exploration. It significantly reduces the reliance on incredibly complex data stacks. You just plug Metabase into your new PostgreSQL world, and the agents can see everything clearly.
The overarching goal here is removing friction. You build the huge Kafka pipes to move the data, you optimize the hardware limitations with GreenBoost, and you standardize the storage environment with PostgreSQL and Metabase.
You create a perfectly frictionless, standardized environment for the software to operate in.
Exactly.
All right, so we have the massive pipes, and we have the database infrastructure completely ready to go. The table is set. Now, big tech companies are taking the training wheels off their agents and letting them run wild in these perfectly frictionless environments.
Yes, they are.
Meta is using what they call their ranking engineer agent to accelerate ads ranking innovation.
The ranking engineer agent is a fascinating case study in complete delegation. It is designed to manage the full machine learning lifecycle.
Wow.
We are talking about everything from feature engineering and training to evaluation and deployment. And it does this with almost zero human input.
They use something called the Confucius framework for persistent state. From my understanding, a persistent state means the agent actually remembers its past experiments so it does not make the same mistake twice.
Yes, the persistent state gives the agent a memory. It operates on a three-phase planning framework. First is validation, where it autonomously checks the mathematical feasibility of a new idea.
Okay.
Second is combination, where it figures out how to merge those new ideas with the existing production models. And third is exploitation, where it pushes the successful models directly to production. It even handles its own execution errors autonomously using automated runbooks.
But hang on, I have to push back here. If an agent is acting entirely autonomously, validating its own ideas and pushing them to production, who exactly is checking the checker? If it hallucinates a terrible idea, but mathematically convinces itself it is brilliant, what stops it?
That is the most pressing question in the entire field right now. Meta has implemented strict compute budgets to artificially constrain the agent so it cannot burn millions of dollars in server costs on a bad idea.
Okay, at least there is a budget.
But the operational autonomy is still vast. The system is fundamentally designed to generate high-quality hypotheses from historical insights without asking a human for permission.
It is a massive leap of faith. And Dropbox is doing something similar to optimize their internal systems. They are using a framework called DSPy to optimize the relevance judge for their Dash search product. A relevance judge is the system that decides if the search results you're looking at are actually useful.
Right. DSPy is a framework that algorithmically optimizes how you prompt language models. Instead of a human engineer sitting there tweaking a text prompt to get a better answer from the agent, Dropbox used DSPy to define a clear mathematical objective.
Yeah.
They wanted to minimize the normalized mean-squared error against human judgments.
Let us unpack that because it sounds like heavy jargon.
Mm-hmm.
Instead of a human tweaking a prompt, the system mathematically calculates how far off the agent is from a perfect human answer and adjusts itself. How does that mechanism actually work?
Well, you provide a golden data set of perfect human answers. The system turns the agent output into a mathematical vector and measures the geometric distance from that perfect answer.
So literal distance.
Yes. The larger the distance, the higher the error. DSPy iteratively rewrites the instructions it gives the agent, running thousands of micro-experiments trying to shrink that mathematical distance down to zero.
That is wild. They incorporated structured feedback, enforced strict JSON validity guardrails so the output was always formatted correctly, and let the iterative prompt refinement run.
And it worked.
Yeah, the mechanism allowed them to generate 10 to 100 times more synthetic labeling at the exact same cost. They shrank their model switch times from weeks of human labor down to just 1 or 2 days.
The velocity increase is undeniable. When you remove the human bottleneck from the prompt engineering and the evaluation phases, the system moves at the speed of compute.
But that lack of human input is exactly where the dream turns into an absolute nightmare. The agents are incredibly fast, but the actual quality of the final output is tanking.
Unfortunately, yes.
We are seeing heavy reliance on coding tools at companies like Anthropic, Amazon, Uber, and Meta. Engineers classified as power users of these artificial intelligence tools produce 52% more pull requests. They're writing code at a staggering pace.
But software quality is actively declining across the board. The volume of code is up, but the integrity of the code is faltering terribly.
Right.
Anthropic, for instance, has over 80% of its production code generated by artificial intelligence, and that is resulting in critical user experience bugs that are impacting millions of people.
Amazon is seeing a massive rise in severe incidents, and they now mandate senior engineer review for all artificial intelligence-assisted code.
Yeah.
So the junior engineers use the agents to write the code faster, and the senior engineers spend their entire week fixing it.
The causality here is crucial to understand. The agents lack broader architectural context. They can write an isolated function perfectly,
Sure, give them a math problem, they nail it.
but they fundamentally fail to understand how that single function interacts with a legacy database 5 layers deep in the corporate infrastructure.
It reminds me of the reports on Claude Code. It is a great companion for rapid prototyping, but it completely lacks judgment for unsupervised production work. It gives these incredibly confident but entirely wrong outputs.
Yes, the hallucinations.
It causes silent data loss where it overwrites a file without telling you. And it suffers from non-determinism, where it gives you a completely different answer every single time you ask it the exact same question.
Which is maddening for debugging.
It is exactly like having an overconfident intern who accidentally deletes the production server, but smiles brightly while telling you about what a great job they did optimizing the folder structure.
That is painfully accurate. The overconfidence is an inherent artifact of how the underlying models are trained. They are mathematically rewarded for being helpful and assertive, not for expressing doubt.
Which is terrifying.
And this issue scales up dangerously. The Gartner Data and Analytics Summit highlighted that the write-heavy trajectory data generated by these agents is straining traditional operational databases to their breaking point.
Trajectory data being the intermediate steps, the digital scratch pad, and the massive logs the agent creates while it is supposedly thinking through a problem.
Correct. Every time the agent pauses to evaluate a path, it writes a log. Because it happens so fast and at such an extreme volume, unmanaged models are creating massive artificial intelligence blind spot debt.
Oh, wow.
It is completely blurring the boundaries between core infrastructure and feature stores, making enterprise governance incredibly urgent right now.
I have genuine skepticism about this push for pure velocity over quality. Is there any actual return on investment here? Or are we just generating garbage faster than we ever have in human history?
The return on investment does exist, but it requires highly constrained, highly specific applications. OpenAI managed to scale their PostgreSQL architecture to 800 million users using these exact tools.
Okay, so there are wins.
Yes. Insurance companies are leveraging 95% accurate speech-to-text models to rapidly create patient care plans. So the value is very real, but the semantic integration challenges remain completely unresolved.
Semantic integration meaning making sure the agent actually understands the meaning and consequence of the data it is altering, rather than just moving words around.
Precisely. Until the agents understand the real-world consequence of their actions, the quality will remain erratic.
Well, mate, it gets worse. It is not just that the agents are writing buggy code that senior engineers have to spend their weekends fixing. They are actively compromising external security.
Yes, the security aspect is alarming.
GitGuardian just reported an 81% surge in artificial intelligence service leaks.
The scope of the exposure is staggering. Nearly 29 million secrets were exposed on public GitHub repositories.
29 million.
Yes. The widespread adoption of artificial intelligence-assisted coding drove a 34% overall surge in leaked secrets across the entire industry.
Just to clarify for you listening, a leaked secret means an API key, a database password, or a secure credential that gets accidentally left in the raw text of the code and uploaded to the public internet. Claude code commits have a 3.2% leak rate, which is over twice the baseline for normal human errors.
And the internal risks are arguably even higher. Internal corporate repositories were found to be 6 times more likely to contain hard-coded secrets.
Wait, really? 6 times?
Yes. Because developers assume their internal code is behind a firewall and therefore safe, they let the agents hard-code passwords directly into the scripts to save time.
That is just lazy.
It is. Furthermore, 64% of valid secrets exposed from past historical data remain completely unrecalled by security teams.
They are just sitting there, fully active, and waiting for a malicious actor to exploit them. And beyond just leaked credentials, we have active, hostile vulnerabilities being introduced. Modern agents like Snowflake Cortex, Copilot, and Slack are highly vulnerable to prompt injection attacks.
A prompt injection attack is when a malicious instruction is cleverly disguised as normal user input. Because these autonomous agents execute actions based on text parsing, a specifically phrased input can completely bypass their internal safeguards.
Oh, I see.
We have a documented real-world example where an injected prompt tricked Snowflake Cortex into escaping its secure sandbox environment.
So let me get this straight. We built petabyte-scale pipes, we tricked our hardware into running these massive models, and we gave the agents total autonomy. And the result is that the agents are writing buggy code, they are leaking our database passwords to the entire internet, and they are executing external malware.
Unfortunately, yes. In that specific Snowflake Cortex incident, the injected prompt executed malware without any user approval, allowing the attackers to steal or destroy data using the security credentials of the actual victim.
That is a total nightmare.
When you give a system the autonomy to query databases and write code on your behalf, a successful prompt injection means the attacker automatically inherits all of those high-level permissions.
If artificial intelligence is writing the code and also fixing the bugs, how long until human engineers are entirely locked out of understanding their own infrastructure? Keep questioning the code, and thank you for exploring with Vocal Technologist.
Spoken Tech for your ears.